So good morning, everybody, to this session. The next speaker is Urs Lang from ETH Zürich. He will speak on a combinatorial higher rank hyperbolicity condition. Thank you.
Yes, so thank you. Thanks to the organizers for inviting me to speak. I'm sorry I cannot be there. So what I'm going to talk about is part of a program which started with this paper with Bruce Kleiner, and now there are two more papers with two students, Tommaso Goldhirsch and Martina Jürgensen. And today I'm going to talk mostly about this last paper, but some of the results are based on the earlier papers. So what do we mean by higher rank hyperbolicity? So the overall goal is to prove that everything we know about Gromov hyperbolic spaces has some higher rank analogs. So analogs in spaces of higher rank. And as in previous talks, so the model spaces one should keep in mind here are the higher rank symmetric spaces of non-compact type. But we want to build a theory of metric spaces and to give a systematic treatment of such higher rank analogs. So we need a more general definition of rank. And an appropriate definition of rank in this context is the asymptotic rank. So this is defined as follows: take a metric space, and then the asymptotic rank is the supremum of all integers greater or equal to 0, for which there exist sequences, so a sequence of scale factors going to infinity, and a sequence of subsets, yk in x, so that if, well, you look at the rescaled sets, right? So you should think of these sets as being bigger and bigger, and you somehow rescale these sets to unit scale. And then you look for a Gromov-Hausdorff conversion sequence. So you want this sequence of rescaled sets to Gromov-Hausdorff converge to a typical n-dimensional object. And there are different choices here which lead to equivalent definitions. So you can take the unit ball in some n-dimensional norm space, for example. So this somehow means that, well, you look at larger and larger sets, and if you rescale, this will converge to something n-dimensional. So this goes back to Gromov in his paper on asymptotic invariance, and then it was further investigated by Kleiner and Wenger and Steckong. So maybe this definition is not so easy to grasp, but it has nice properties. So it's a quasi-isometry invariant for general metric spaces. So that's in the paper by Wenger. And a more concrete case is maybe the following. So if X is a cat-zero space or a metric space satisfying a weaker convexity condition, so here you take so-called conical geodesic bicombing. So I will also use this later on. So I'll give the definition here. So geodesic bicombing is simply a map which selects for every pair of points xy in, pair of points xy, geodesic constant speed, minimizing geodesic from x to y. So connecting the 2 points. And we call geodesic bicombing conical if it satisfies this inequality here. So this will be in particular this will be satisfied in particular for cat-zero spaces and also for Busemann convex spaces. Right, so you can think of this as being a weak notion of non-positive curvature. So in this situation, if X is proper and co-compact, then the asymptotic rank is equal to the maximal n, so that X contains an isometric copy of Rn. So in the case of cat-zero spaces, so maximal dimension of a flat contained in the space, or in this more general situation with conical bicombings, the maximal n, so that you find an isometric copy of some n-dimensional norm space. So maybe that's an example to keep in mind for this definition of the asymptotic rank. Now, I would like to give you a sample result for this theory of higher rank hyperbolicity. And so we need one more definition. We say that the metric space has a slim simplex property, SSN, if the following holds. So you take a Euclidean n+1 simplex, so just simplex in Rn+1, so convex hull of n+2 points in general position. And you look at a map on the boundary of this simplex. And the condition is that whenever you restrict your map to one of the facets, so facets are codimension 1 faces, then it's a lambda C quasi-symmetric embedding. So, well, the definition of lambda C quasi-symmetric embeddings has been mentioned many times already. So that's somehow the high rank analog of a quasi-geodesic triangle, right? You have a simplex and your facets are mapped by quasi-symmetric embedding. And so we say that the metric space satisfies a slim simplex property if the image of every facet is within distance d of the union of the images of the remaining ones. So in that sense, this map is somehow slim, right? So that's an analog of the fact that in the Gromov hyperbolic space, quasi-geodesic triangles are slim, right? And it's obviously a quasi-symmetry invariant condition, so that's a good condition. And you could take this as a definition of higher rank hyperbolicity. Now there's the following result. So the bulk of this is in the paper with Bruce, and in this form it's in the paper with Tommaso. So if n is greater or equal to 1, and X is a proper metric space with a conical geodesic bicombing, then the asymptotic rank is at most n if and only if X has a slim simplex property. So, and the constant can be taken of these forms. So there's a constant depending on X and n, and on the multiplicative quasi-symmetry constant, lambda, and then you simply multiply by 1 plus c. Okay. So actually, in the paper with Tommaso, we have a list of 6 different properties, all of which are equivalent. And these are only 2 of them, but the other conditions are a bit more complicated to state. So I'll just restrict to these 2 conditions. And there is also a uniform version of this, which is used later on. So if you look at the class of such metric spaces X, so proper metric spaces with conical geodesic bicombings, then this inequality, well, this equivalence also holds uniformly. So this means that the asymptotic rank of X is at most n uniformly for all X in C. And by this, we mean that, well, in the definition of the asymptotic rank, we take the subsets. We can take the subsets in different members of the class, right? So you can take a sequence in the class, and then you take subsets in the corresponding elements of the sequence. And then this will hold uniformly. So this holds if and only if every X in the class, again, has a slim simplex property. And the benefit of this is now that the constant here depends only on the class and not on the individual member of the class. And this can be useful because if your class is defined without any further parameter, then the constant will only depend on n and lambda, right? And nothing else. So, yeah, I told you that in this paper with Tommaso, we have a list of 6 different properties. So what is missing in that list is an analog, higher rank analog of Gromov's quadruple definition of hyperbolicity, which I will state later on. So we were wondering what could be an analog of this. And in order to describe this, I need some further terminology, and I need to remind you of injective metric spaces and combinatorial dimension. So a metric space is injective if every one Lipschitz map defined on a subset of a metric space B. So no matter what A and B is, can always be extended as a one Lipschitz map into X. So one Lipschitz maps into the space can be extended as one Lipschitz maps always. So the terminology comes from the fact that that's really, well, X is an injective object in the category of, in the metric category of metric spaces with one Lipschitz maps as morphisms. And there are many examples, so the real line, L infinity for any set S, complete R-trees, and then you can also take L infinity products of injective metric spaces. But there are many more. So, and there are the following properties. So that's a very old result, classical. X is injective if and only if X is hyperconvex. So this terminology was introduced in this paper by Aronstan and Panish Bhakti from the 50s. Every family of closed poles, so that the sum of the radii of two of them is greater or equal to the distance of the centers, has non-empty intersection. So this means that, well, in a geodesic metric space, it means that if you have a family of pairwise intersecting balls, then the family will have non-empty total intersection. As a consequence of this, every closed ball in an injective metric space is again injective. And every injective metric space has a conical geodesic bicombe, and it has further properties. It's also reversible. So the geodesic selected by the bicombe from Y to X is the same as geodesic from X to Y, traveled in the opposite direction. And it's also equivariant, so compatible with the isometries. And furthermore, if X is injective and you have a group of isometries with bounded orbits, then there is a non-empty fixed point set. So there are global fixed points, and the set of all these fixed points is again injective. So that's a result which should remind you of a completely analog result for cat-zero spaces, right? And in fact, these two last properties here can be viewed as, well, some of these last two properties show that injective metric spaces share some properties with spaces of non-positive curvature. So it's a good class of spaces. And the nice fact is that every metric space has an injective hull. So yeah, every metric space is contained in kind of smallest injective metric space. So the notation is like that. So that was discovered by Isbell. It's a really remarkable fact. So EX is an injective metric space. E is an isometric embedding. And EX is smallest in the sense that, well, this universal property here holds whenever you have an isometric embedding of X into some injective metric space, then this will factor in this way, right? Factors through EX. It's a universal property. And there is an explicit construction which was given by Isbell, so I'll repeat briefly. So first one looks at functions, real valued functions on X, so that the sum, well, fx plus fy is greater or equal to the distance of the 2 points. So this should remind you of the triangle inequality. And indeed, the idea is that, well, you extend your metric space, so and the new points are functions on the space. And the value of the function at the point X, this will be exactly the distance of the new point, namely f, to the point X. So fx will be the distance of in the injective hull of between f and x. Okay, so that's the idea of the construction. And now we take the natural partial ordering on delta x, and you take all minimal elements. Can also be characterized like this. And then you can put the metric, you simply take the L infinity metric. So it turns out that, well, these elements of EX are not necessarily bounded. So, well, typically they are not, unless X is itself bounded. But it turns out that the difference of two elements of EX is finite. Well, it has a finite subnorm. Difference is bounded. And so this will define a metric on EX. And the canonical embedding is, of course, the function which takes X to the distance function, EX. So that's the construction. And this has nice properties. So if X is compact, then so is EX, the injective hull. So that's essentially just a consequence of the Arcela-Ascoli theorem, because these elements of EX are one Lipschitz. And if you look at this operator, so compact metric space is sent to its injective hull, which is again compact. This turns out to be two Lipschitz with respect to the Gromov-Hausdorff metric. And constant 2 is optimum. And if X is finite, then the injective hull is a finite polyhedral complex of dimension at most 1/2 times the number of points, with L infinity metrics on the cells. So if you start with 3 points, then you get a tripod. And if you start with 4 points, then you get something more complicated. There is a 2-dimensional cell, which is kind of a rectangle with an infinity metric and some antennas attached at the corners. And then for 5 points, there are already different combinatorial types. And then if you go on, then it kind of explodes. So for 6 points, there are over 300 different combinatorial types. And so on. But in any case, it's a finite polyhedral complex with L infinity metrics on the cells. So these are injective hulls. Now, I would like to, for what I'm going to do, I would like to start from the following basic observation. So for a metric space X, the following are equivalent. X embeds isometrically into a tree. And here by tree, I mean the most general kind of tree, R tree, right? Geodesic metric space, so that every geodesic triangle is a tripod. And so this is equivalent to the following condition. Well, every quadruple of points satisfies this inequality. And so there are 3 ways of forming such sums of 2 distances in the quadruple. And this inequality tells you that the 2 largest one of these sums are equal. And so I don't know who observed this first. So there are some references in around 1970 in computer science literature and discrete mathematics. And then Dress in 1984, he rediscovered Isbell's injective hull construction, and he showed that one can also add this condition here. So this is also equivalent to the combinatorial dimension of X being at most 1. And the combinatorial dimension is simply defined as the soup of the dimensions of the injective hulls of finite subsets. Right, so we know that for a finite subset, we get a nice polyhedral complex, so we know what the dimension is. And we take the soup over all of all these dimensions. So here, the idea is somehow that you look at the finite subset and then you use the dimension of this injective hull as a rough measure of the complexity of the metric on this finite set. Right, so if your finite set embeds into a tree, then the dimension of the injective hull will be 1, or at most 1. And so that's somehow a combinatorially simpler case. And otherwise, maybe your finite set embeds at best in a 2-dimensional complex, and the combinatorial dimension is 2. So certainly here, if X embeds isometrically into a tree, then if you take a finite subset, this will also embed into a tree, and so trees are injective, and so the combinatorial dimension will be at most 1. And the converse also holds. So that's an equivalent statement. And now there are 2 generalizations in the literature. So one is in the paper by Dress. So he actually shows that for n greater to 0, so for any n, the combinatorial dimension is at most n, if and only if X satisfies a certain 2 times n plus 1 point inequality. I will state it on the next slide. Yeah, so that's a bit, we'll see it. Okay. And there's another generalization, namely Gromov's definition, right, of delta hyperbolicity. So for delta greater equal to 0, X is delta hyperbolic if this inequality here holds in a relaxed form with an additional +2 delta on the right side. So that's, well, Gromov stated it as an inequality for the Gromov products, but this inequality here is equivalent. So this happened about the same time, right? 84, 87. And in fact, it's quite interesting. If you look at Gromov's paper, if you look at the references, he cites the preprint version of Dress's paper, but he didn't really make full use of it. And well, we were wondering what could be an analog of Gromov's quadruple definition in higher rank. And here we already have this inequality involving 2 times n plus 1 points due to Dress, right? And so the most naive thing is just to combine the two things. So what do we get if we combine 1 and 2? So at first we just did it for fun, but then it turned out that it works really well. So that's what we do. We simply take these two facts, and we take Dress's inequality and we add a 2 delta on the right side. So here is how it looks like. It's a kind of an experimental definition. So we need an index set containing 2 times n plus 1 elements, and we choose this set here because then there's a canonical involution, namely changing the sign. And we fix delta greater or equal to 0. Then we call a metric space n delta hyperbolic if for every family of 2 times n plus 1 points, there's a permutation which is different from this canonical involution minus identity of the index set, so that this inequality holds. Right? So you could also write this as a max. Here I'm saying that there exists a permutation alpha. So this sum here is less than or equal to the max of all these possible sums over all such permutations. So this looks kind of similar to the case n is equal to 1, right? And so indeed, so if x is n0 hyperbolic, so that's again the case for delta is 0, if and only if the combinatorial dimension is at most n. So that's precisely Dress's result. So that's the result in Dress's paper from 84, except that he didn't use this terminology of n0 hyperbolicity. So he just wrote down this inequality. What does it mean in case n is 0? Well, if n is 0, then there is no then there are only 2 points involved, right? And there is no permutation different from, well, every permutation different from minus identity is simply the identity. But if you take alpha equal to the identity, then the sum is 0, right? And so here on the left, you have the same term twice. So you have x1, x minus 1, and x minus 1, x1, right? And here you have 2 delta. So a metric space is 0 delta hyperbolic if and only if the diameter is at most delta. That's a kind of trivial case. And then, indeed, x is 1 delta hyperbolic if and only if x is Gromov delta hyperbolic. So here is again the condition. Well, first, if, I wanted to explain this, it's a bit tricky. But if this inequality holds, so this inequality here holds, then you simply add the left-hand side again on both sides. Then on the left-hand side, you get this sum, right? So every term occurs twice. And on the right-hand side, you get the sums corresponding to some cyclic permutations. And you take the maximal one, and then you get this inequality here. And conversely, if this inequality holds, well, first you can prove that for n greater or equal to 1, it's enough to look at fixed point free permutations. And then there are 5 possibilities. So here we have the 4 points. That's a symbolic picture. So an edge stands for a term in the sum, right? So if you restrict ourselves to fixed point free permutations, then we have these 5 possibilities. So the orientation here, I should also draw arrows, right? But the orientation doesn't matter for the sum. So I can ignore it. So these are the only possibilities. And well, if we are in the first two cases, then you can simply subtract the horizontal edges. So on the left, we have simply 2 times the horizontal edges. So to correspond to this sum. And then, yeah, if this sum here on the right is one of these two, then you can simply subtract the horizontal edges. And then you get either x1, x2 plus x minus 1, x minus 2, or the other sum corresponding to the diagonals, right? If the right side is this graph here, well, then you can see that you can do better. So depending on whether the sum corresponding to the cross or the 2 vertical sides is bigger, we can pass to one of these. And then, so this reduces this third case to the last case where we have an involution of this form. And in this case, you can simply divide the inequality by 2. And then you are left with once the vertical edges or once the cross again, and you get again this inequality even with a delta in place of 2 delta. So I'm not sure this was understandable. So this was an attempt to explain this equivalence, right? So here's a list of basic properties. Well, there are some obvious monotonicity properties. Every n delta hyperbolic space is, of course, n prime delta hyperbolic for all n prime greater or equal to n and delta prime greater or equal to delta. It behaves well under products, L infinity products. So if you take the L infinity product of 2 spaces, namely ni delta hyperbolic space, so to say the same delta, then this will be n1 plus n2 comma delta hyperbolic. And the proof is actually contained in Dress's paper for delta equal to 0. You can just take it from there and add deltas, and then you get it. So in particular, the L infinity product of n delta hyperbolic spaces is n comma delta hyperbolic. So that's a good thing, but it's restricted to L infinity products. So this notion of n delta hyperbolicity has a clear L infinity flavor, which you cannot see for n equal to 1, right? Because in 1 dimension, there's no difference between Euclidean and L infinity norms. You may ask, well, is it preserved on the quasi-isometries? Well, not quite. For a certain class, it will be, and we'll see it later on. But in general, for metric spaces, n star hyperbolicity, so we write n star if we don't want to specify the delta. Right? N star hyperbolicity is preserved under rough isometries. So this means 1, c quasi-isometries for c greater or equal to 0. So the multiplicative constant is 1. What about norm spaces? Well, that's actually a statement about the combinatorial dimension. So a norm space is n0 hyperbolic if and only if it is finite dimensional with a polyhedral norm. And you can tell what the dimension, what the n is. The minimal n is the number of pairs of opposite facets of the unit ball. And so every n0 hyperbolic space, norm space, has dimension at most n. I should have said, of course, if you have an n delta hyperbolic norm space, then you can rescale, and then it will also be n0 hyperbolic. So the only n0 hyperbolic n-dimensional norm space is L infinity n. So Rn with the sup norm. And the asymptotic rank is at most n for n delta hyperbolic space. So again, this also holds uniformly. And every asymptotic cone, if you know about asymptotic cones, of a sequence of pointed n delta hyperbolic spaces is n0 hyperbolic. So that's a simple rescaling argument. Now, a very nice fact is that, well, we can look at injective halves of n star hyperbolic spaces. So if x is n delta hyperbolic, then so is ex. So this condition passes to the injective half with the same delta, same n and same delta. So that was known for the case n equal to 1 for the Gromov hyperbolic case. And it's a very useful fact because you can somehow if you have a general metric space which satisfies this quadruple condition, then this provides a very efficient way to embed it into a much nicer hyperbolic space. So preserving the delta even. So, because then the injective hull will be geodesic, so and injective, so it has this bicomb, general conical bicombing, and has more properties. So what does it mean, right? So we started from the combinatorial dimension, so this inequality characterizing combinatorial dimension, and we added a 2 delta on the right side. So intuitively, a metric space should be n delta hyperbolic if and only if the injective hull contains no large n+1 dimensional sets. So that's somehow the intuition. And we can quantify this. So we use the following sets. So these are kind of model sets in Rn+1 with the subnorm. Simply the points at distance s on the coordinate axis, right? So, well, the injective hull of these sets, they contain the ball of radius s half, which is actually the cube, right? So the ball in L infinity, this kind of cube. So in dimension 3, the picture is the following. So here, the injective hull will be a rhombic dodecahedron. So the original points are these acute vertices here, the tips of this rhombic dodecahedron, and then there are additional vertices, and these additional vertices, they span a cube. Right? So that's the picture in dimension 3. Now we have the following result. Well, if X is n delta hyperbolic, then the injective hull contains no isometric copy of the set for S greater than delta. Conversely, if EX contains no isometric copy of the set for S greater than delta, then, well, X, we cannot prove that X is n delta hyperbolic, but it's n, n delta hyperbolic. So this somehow quantifies this intuition here. And, well, in some special cases, this gives optimal results. So if delta is 0, well, this tells you that X is n0 hyperbolic if and only if there is no isometric copy of the set for S positive, right? And one can easily check that this condition is equivalent to the combinatorial dimension being at most n. So this actually reproduces Stress's result. And you can think of this proposition 2 as a kind of stable version of this result due to Stress. And if you look at the case n equals 1, then you see that X is Gromov delta hyperbolic if and only if the injective hull contains no copy of the set for S bigger than delta. So if n is 1, then it's really an if and only if, right? So that was, of course, known, but you get it here as a special case. So here's a kind of a summary of what we have achieved so far. So it's a statement for general metric spaces X. So the following are equivalent. X is n star hyperbolic. The injective hull is n star hyperbolic. The asymptotic rank of the injective hull is at most n. And there is a constant R0 so that EX contains no isometric copy of all of radius R in this L infinity space for R bigger than R0. So again, it's for general metric spaces, and so you cannot expect much, right? But you can use the injective hull as a kind of a regularization for X, and then you have these equivalent statements. And the proof is simply we combine the results we have, right? So 1 implies we can prove the cycle. 1 implies 2 by proposition 1. Then n star hyperbolic spaces have asymptotic rank at most n. And then from here to here, that's just the definition of the asymptotic rank. And from 4 back to 1, you can use proposition 2. Right. And so what about the slim simplex property? Well, this holds in a completely general form. So every n-delta hyperbolic metric space has the slim simplex property for some constant, which now depends only on n, delta, lambda, and c, right? But not on x. So note that there are no conditions on x here, except that it's n delta hyperbolic. And so why does it work in this generality? Well, we can use the injective hull. So we take such a map as in the definition of this property, slim simplex property, and we view X as a subset of the injective hull, and then it's easy to approximate it by a Lipschitz map to make it nicer and to make the image compact, right? So then the image is compact, and it's n-delta hyperbolic because EX is n-delta hyperbolic, and it's a subset, so it's still n-delta hyperbolic. Now I use the fact that EY is injective, so it has a conical geodesic bicombing, and also the asymptotic rank is at most n because it's n-delta hyperbolic, right? And this also holds uniformly for all n-delta hyperbolic spaces Y. So we are in the position to apply theorem 1, so the result I mentioned at the beginning. So the point here is really that one can use the injective hull and just do the estimate in the injective hull. So question, when does the converse hold? And so that's, of course, kind of an analog of what we know for Gromov hyperbolic spaces, right? And we would like to know when the converse holds. So it turns out that the good class of metric spaces is the class of coarsely injective metric spaces. So let me briefly define this. Well, there are the following equivalences. So for every metric space, the following are equivalent. So there is a coarse version of injectivity. There exists a constant C, so that every one Lipschitz map into the space can be extended as a rough one Lipschitz map. So here by 1, C Lipschitz, I mean, again, just an additive constant C on the right side, right? Like in the definition of quasi-isometries with multiplicative constant 1, right? So there's an additive error of C. So that would be like a coarse version, rough version of injectivity. And then there is also a corresponding coarse version of hyperconvexity. So the equivalence of these two statements is somewhat the exact analog of this old result by Aronson and Panish-Bhakti. Injectivity and hyperconvexity are the same, and it also holds coarsely. So this means that, well, again, you have a family of poles, and you have this condition, sum of radii is greater or equal to the distance of the centers. Then if you increase the radii by C, the family will have non-empty intersection. And there are more conditions. So EX, the injective hull, is within finite distance from the image of the canonical embedding. And X is roughly isometric to an injective metric space. That's also equivalent. So that's a good result because somehow it shows that this terminology is kind of non-ambiguous. Right? So, because being coarsely injective really means that it's the same as being roughly or coarsely isometric to an injective metric space. So I like this result, and I like this class of spaces essentially because this proposition has been overlooked for some time. So there's this paper on Helly groups by these authors, and they prove that 2 is equivalent to 3. And the funny thing is that for geodesic Gromov hyperbolic spaces, well, these properties hold, and 1, 2, and 3 have been established individually in 3 different papers. So an old paper of myself and some other papers, but we haven't realized that the properties are actually equivalent. So we have overlooked this fact. And I think it's a very good class of spaces. So indeed, for this class of spaces, everything turns out to be very nice. So for coarsely injective metric spaces, we have this equivalence. These equivalences: X is n star hyperbolic, X satisfies the slim simplex property, asymptotic rank is at most n. And there's a last condition for all epsilon that exists R0, so that there is no 1, epsilon quasi-symmetric embedding of L infinity ball of dimension n+1 into X for R bigger than R0. And in particular, this shows that n star hyperbolicity is a quasi-symmetry invariant for this class of coarsely injective metric spaces. So that's because 2 and 3 are clearly quasi-symmetry invariant, right? Right, so maybe I'll skip the proof. Now, there are some applications. So we can combine these results with some recent work in geometric group theory. So there's the work on Helly groups. So a connected locally finite graph with vertex set V. Well, you look just at the vertex set as a discrete metric space is the canonical integer valued metric, right? So this is called a Helly graph. If, again, we have this kind of ball intersection property, every family of pairwise intersecting combinatorial balls has non-empty intersection. So that's a notion which has been around in geometric graph theory for some time. And then one can prove that V is coarsely injective. So in fact, that's already a good approximation of an injective metric space. And it turns out that the injective hull is within distance 1/2, very close. So V is coarsely injective, and the injective hull is proper due to the fact that the graph is locally finite. And then in this paper by Chalopin, Shepoy, Genevois, Hirai, Osaida, they define the class of Helly groups. These are groups acting geometrically, so properly discontinuously, co-compactly, isometrically, so like graph isomorphisms on some Helly graph. And hence, they will also act on the injective hull in the same way. Okay. And well, this is somehow the paper which contains definitions. It's not yet published, so it's a preprint, and this one already appeared here. So there are many classes of groups which are now known to be Helly groups. So, of course, hyperbolic groups are Helly groups. So this essentially follows from result of myself. And then in this paper by Huang and Osaida, they prove that many Archean groups and Garside groups are Helly. And also in this paper by Hertel, he actually proves that all Garside groups, and in particular all braid groups, are Helly groups. And in this paper, they also show that Helly groups have some, they are bi-automatic, for example, so they have some important algorithmic property. And the corresponding result for cat-zero group is not, cat-zero groups is not true. So there are cat-zero groups which are not bi-automatic, by some recent examples. And so this seems to be a good class of spaces. And it turns out that they are n-star hyperbolic in a certain sense. So if you have a group acting geometrically on a proper injective metric space, for example, a Helly group, then the asymptotic rank, well, in this case, group is quasi-symmetric to X, right? And so the asymptotic ranks are the same. So this will be finite. And it decreases the minimal integer so that X is n-star hyperbolic. And then G will also satisfy the slim simplex property and so on. There are more characterizations. And there is no free abelian subgroup of rank n+1. So that's one connection. Another class of groups which has been promoted quite a lot is the class of hierarchically hyperbolic spaces or groups. So that's in a series of papers by Berstock-Hagen and Sisto. That's a kind of axiomatization of some results by Maser and Minsky on the mapping class groups. And well, the definition is very involved. It fills several pages, so I will not state it. But by definition, every hierarchically hyperbolic space has a finite rank. So, and in the case of a hierarchical hyperbolic groups, that's kind of a special case. This rank agrees with the maximal dimension of a quasi-flat in the group. Okay. Now, luckily, there is a recent paper by Helly and Petit, and they show that every hierarchical hyperbolic space can be equipped with a coarsely injective metric, which is quasi-isometric to the given metric. And so, using this, we can state the following corollary. So, if XT is a hierarchical hyperbolic group, or more generally, a hierarchical hyperbolic space with some extra condition, which Bachelor and Sister call asymphoric, then, and we take one of these metrics, so provided by the Helly-Petit paper, then it turns out that the rank of the hierarchical hyperbolic space is actually equal to the asymptotic rank. And this is also the minimal integer, so that X rho is n star mu star hyperbolic. So in particular, we can go back to the original metric, right? Because slim simplex property is a quasi-symmetry invariant, and then we can conclude that every hierarchically hyperbolic group satisfies a slim simplex property in the dimension of the rank of the group. So, and lastly, symmetric spaces. So, of course, somehow the prime model of higher rank spaces are the symmetric spaces of non-compact type and higher rank. So, in rank 1, of course, they are Gromov hyperbolic and hence 1 star hyperbolic in our terminology. And in higher rank, this will no longer be true, right? Because then there are 2 flats, and the Euclidean flats are not. So if you have rank 2, then a 2 flat will not be 2 star hyperbolic. We had this characterization of n star hyperbolic norm spaces, right? So the question is whether you can put a metric on the symmetric space so that it becomes n star hyperbolic. And again, luckily, there is a paper by Helly from 21, and he shows that all classical irreducible symmetric spaces of non-compact type, except those of type SL. So this means essentially that G is equal to SL NR or SL NC. They can be endowed with a coarsely injective G invariant Finsler metric, which gives an L infinity metric on the maximal flats. So he proves it first for the symmetric space of GLNR, which has rank n. And then he proves that, and then there's an embedding result, right? And then he generalizes to the other ones. So if you look at the classification of symmetric spaces, then there are those that are associated to automorphism groups of bilinear forms or sesquilinear forms. And there are a few other ones, namely those of type SL, and you have to exclude those. So, but for all the other ones, it works. So we have these invariant Finsler metrics which restrict to L infinity metrics on the flats. And so if you take such a metric, then it works out nicely. So then, with respect to this Finsler metric, the symmetric space is n star hyperbolic. So my time is up. I should, and it's indeed the last slide, right? So I should stop here. So to conclude, well, we have this notion of n star hyperbolicity, and this has a kind of a definite L infinity flavor. But it turns out that for good classes of spaces like these coarsely injective metric spaces, everything turns out to be nice. And now there are more and more results showing that some important classes of groups or spaces can actually be equipped with coarsely injective metric spaces. So at least for these classes of groups, we get a good theory of n delta hyperbolicity. So maybe ultimately the true notion of n delta hyperbolicity should be quasi-isometry invariant, right? And it's not here, it's not true in general. So maybe the true notion would be to be quasi-isometric to what we defined here, or something like that. But maybe we should still wait a little bit and wait for more results, then we'll see. So I'll stop here. Thank you.
So thank you.